Have you ever wondered what happens when light shines through a window? It seems simple enough. The light just passes right through. But the journey of light is far more fascinating than it appears. When light, which is an electromagnetic wave, travels through any material, it interacts with the atoms and electrons inside. Think of it like a dance. In most ordinary materials, like glass or water, this dance is pretty straightforward. The material responds to the electric part of the light wave and to the magnetic part, but these responses are separate. This interaction is what determines how fast light can travel through the material, which we measure as its refractive index. It's what makes a straw in a glass of water look bent. Now let's add a twist to this dance. Literally. Imagine materials that are not like simple glass, but are built with a special kind of asymmetry, a handedness. These are called chiral materials. The word chiral comes from the Greek word for hand, because just like your left and right hands, chiral objects are mirror images of each other but cannot be perfectly overlapped. This unique structural property creates a much more intricate dance with light. Instead of just responding to the electric and magnetic parts of light separately, these materials create a remarkable coupling between them. The electric part of the light wave can now create a magnetic response, and the magnetic part can create an electric response. It's a crosstalk that completely changes the rules of the game. To understand this special interaction, scientists use a few key parameters. The first two are familiar permittivity, which describes how a material responds to an electric field, and permeability, which describes its response to a magnetic field. These are the standard rules for the dance of light in any medium. But for chiral materials, we need two more special parameters. The first is the chirality parameter, which measures the strength of that cool electric-magnetic crosstalk we talked about. A higher value means a stronger twist in the material's response. The second is the telegen parameter, which is a bit more exotic and describes a different kind of magnetoelectric coupling, though the chirality parameter is the star of our show today. This special coupling has a profound effect on how light behaves. Specifically, it affects the light's polarization, which is the orientation of its electric field oscillations. Chiral materials are particularly sensitive to circularly polarized light, where the electric field spins in a circle like a corkscrew as it travels. A chiral material will treat left-spinning light differently from right-spinning light. One might travel faster through the material than the other, or one might be absorbed more strongly. This selective interaction is the source of the incredible optical effects that make these materials so exciting for scientists and engineers exploring the frontiers of technology and discovery. So, what exactly is chirality? The easiest way to picture it is to look at your own hands. Hold them up, palms facing you. They are perfect mirror images of each other, right? Now try to lay one hand perfectly on top of the other, palm to palm. You can't do it, your thumbs will stick out on opposite sides. This non-superimposable mirror image property is the essence of chirality. It's everywhere in nature. Think of spiral seashells, twisting vines, or even the molecules of life itself. The DNA in our cells is a famous example of a right-handed double helix. This inherent handedness is not just a curious detail. It dictates how these structures interact with the world around them, especially with light. When light travels through a chiral material, something magical happens. The material's twisted structure forces the light's polarization to rotate. Imagine pushing a spinning top through a dense, spiraling forest. Its path and spin would be influenced by the trees. Similarly, as linearly polarized light passes through a chiral medium, its plane of polarization twists. This phenomenon is called optical rotation. Furthermore, these materials can separate light into its two circularly polarized components, left-handed and right-handed. A right-handed chiral material might allow right-handed circularly polarized light to pass through easily while reflecting or absorbing the left-handed kind. This selective filtering is a superpower that ordinary materials just don't possess. The different treatment of left and right-handed light leads to two different refractive indices within the same material, one for each circular polarization. This is a key departure from non-chiral media, which have only one refractive index. This difference in speed can lead to some truly mind-bending effects. One of the most astonishing possibilities is achieving a negative refractive index. In a negative index material, light bends in the opposite direction to what we normally see. While this effect is complex to achieve, chiral structures provide a unique pathway to engineering materials where both the permittivity and permeability can be negative under certain conditions, a requirement for this backward-bending light. This ability to manipulate light with such precision opens up a universe of possibilities. Think of it as having a set of knobs to tune how light behaves. By designing the handedness and the strength of the chirality in a material, we can control the amount of polarization rotation, filter light with incredible specificity, and even guide it along unconventional paths. This level of control was once the stuff of science fiction. But with the advent of metamaterials, artificially engineered structures designed to have properties not found in nature, scientists are now turning these fascinating concepts into tangible reality, building materials that can perform optical tricks we've only dreamed of. How do we actually build these amazing chiral materials? Since nature doesn't always provide structures with the exact properties we need, scientists have become architects of matter, creating metamaterials. These are not materials in the traditional sense like gold or plastic, but are composed of tiny, repeating structures, each meticulously designed to interact with light in a specific way. For chiral metamaterials, the building blocks are, of course, chiral themselves. Some of the most common designs include arrays of tiny metallic helices, which look like microscopic springs, or twisted wires that mimic the spiral shape of DNA on a larger scale. The fabrication of these intricate structures requires incredible precision and can be approached in two main ways: top-down and bottom-up. Top-down methods are like sculpting. You start with a larger block of material, like a silicon wafer, and carve away the unwanted parts to leave behind the desired pattern. A powerful technique called electron beam lithography, for instance, uses a focused beam of electrons to draw nanoscale patterns, creating arrays of tiny gold helices or other complex shapes with remarkable accuracy. This method gives engineers immense control over the final design, but can be slow and expensive for creating large area samples. The bottom-up approach, on the other hand, is more like biology's way of building things. It relies on chemistry and molecular self-assembly, where tiny components spontaneously organize themselves into larger, ordered structures. Think of how crystals form or how proteins fold into specific shapes. A brilliant example of this is DNA origami. Scientists can design long strands of DNA that, when mixed with shorter staple strands in a solution, fold themselves into predictable, complex, three-dimensional shapes, including chiral structures. These DNA scaffolds can then be coated with metallic nanoparticles to make them interact strongly with light, creating a self-assembled chiral metamaterial. Each of these methods has its advantages. Top-down fabrication offers unparalleled design freedom and precision, allowing us to create metamaterials that work with specific wavelengths of light, from visible to microwave frequencies. Bottom-up self-assembly is incredibly powerful for creating vast numbers of structures at once and can achieve feature sizes far smaller than what traditional sculpting methods can manage. By combining these techniques, researchers are developing hybrid approaches that promise the best of both worlds: the design flexibility of top-down methods with the scalability and molecular precision of bottom-up assembly, pushing the boundaries of what we can build. So, what can we do with these incredible light-twisting materials? The applications are as exciting as the science itself. One of the most immediate uses is in creating advanced optical components. Imagine super-thin polarizers that can selectively filter light based on its circular polarization, which could lead to more efficient displays for our phones and TVs, or even novel anti-glare coatings for glasses and camera lenses. By precisely controlling the rotation of light, chiral metamaterials could also be used to make compact optical isolators, devices that allow light to travel in only one direction, a crucial component for stabilizing lasers and building the next generation of optical computers. Beyond just manipulating light, these materials are also fantastic sensors. Because their optical properties are so sensitive to their structure and environment, even a tiny change can cause a big, measurable signal. For example, a chiral metamaterial could be designed to detect the presence of specific biological molecules, like proteins or DNA. When the target molecule, which is often chiral itself, binds to the metamaterial's surface, it would alter the way the material interacts with light, changing its color or the amount of polarization rotation. This could lead to highly sensitive, real-time biosensors for medical diagnostics or environmental monitoring, capable of detecting diseases or pollutants with unprecedented accuracy. The unique ability of chiral metamaterials to exhibit a negative refractive index also unlocks some truly futuristic possibilities. While perfect invisibility cloaks that hide objects from view are still incredibly challenging to build, the principles behind them rely on materials that can bend light around an object as if it weren't there. Negative index metamaterials are a key ingredient in these theoretical designs. More practically, these materials could be used to create superlenses capable of imaging objects smaller than the wavelength of light itself, breaking a fundamental barrier in microscopy and allowing us to see the inner workings of cells and molecules in stunning detail. It's this incredible potential for discovery and innovation that has scientists so excited. From fundamental physics to practical technology, chiral metamaterials represent a new frontier. They provide a powerful toolkit for controlling light in ways we never thought possible, challenging our understanding of how light and matter interact. As our ability to design and fabricate these complex structures improves, we can expect to see them move from the laboratory into real-world applications. The future of optics might just be a little more twisted, and that's a very exciting prospect for all of us.